Okay, so we continue with our discussion about general varieties, namely projective spaces and projective varieties. So if you recall from the last lecture, what I had told you was that if you take projective space, which is you take affine space of dimension n plus 1 over an algebraically closed field K. So this is, as a set, just Cartesian product of K n plus 1 times, but given the Zariski topology, and then you take away the origin and look at the space of lines, then you get the projective space over K, and there is this map which is the natural projection map. You can think of it as a quotient map, and you can also think of it as associating every point in projective space to the line through the origin that it corresponds to. Okay, and what we saw last time is that this projective space is it can be given the Zariski topology in three ways. One is to take the quotient topology given by this map pi, which makes use of the topology above, the Zariski topology above. The second way of giving the Zariski topology on projective space is to declare closed sets to be of the form given by common zero loci of a bunch of homogeneous polynomials in n plus 1 variables. Okay, and the third way is to consider an open cover of projective space by open sets which are homeomorphic to affine space, and then or which are bijective to affine space, and then transport the variety structure. So it is the third aspect, namely the affine cover of projective space by n plus 1 copies of affine space, which is what I explained last time. So you define the subset Ui. You define subset Ui, which is the locus where xi does not vanish. So basically you have so the coordinates here are x0 through xn. That is how a point here looks like, and well, it goes down to a point here with which will now have homogeneous coordinates x0 semicolon etc. xn. And I am using the same xi to denote both the coordinate functions as well as the coordinates, general varying coordinates, and ui corresponds to xi not equal to 0. This is an open subset because its complement is the 0 set of xi, which is the 0 set of a homogeneous polynomial. Xi is a homogeneous polynomial of degree 1, so it is a complement of a closed set, so it is an open set, but the point is that you have this map phi I from ui to an n dimensional affine space, which is gotten by sending a point with coordinates x0 etc xn to what you do is you divide every coordinate by xi, and then at the entry xi you will get xi by xi, which is 1, and you forget it. So you just send it to the point x0 by xi comma xn by xi, and here you omit xi by xi. So what we saw last time was that this phi is actually an isomorphism of varieties. Okay, so phi is an isomorphism of varieties and what it will induce is pull back by phi I induces a K algebra isomorphism so the K algebra isomorphism will be, say, pulling back regular functions. So given a regular function here, you pull it back to a regular function here. Pulling back means you given a function here, you compose it with this to get a function here. So you get a K algebra isomorphism from the regular functions on an to the regular functions on ui, and the fact is that this is the same as the affine coordinate ring of affine space, and this guy here is can be identified with the homogeneous localization of the polynomial ring corresponding to this affine space at xi, which means that you call S as the affine coordinate ring of affine n plus 1 space, and is also called as the homogeneous coordinate ring of the n dimensional projective space. And what you do is you take that's just the polynomial ring in the variables x0 to xn. You localize it with respect to xi, okay, and S has a grading. There is a natural grading on S, which is given by degrees of polynomials, homogeneous polynomials. Every polynomial in S breaks up uniquely into its homogeneous components, and each homogeneous component has a fixed degree. That is the grading on S, and that grading will induce a grading on this localization by simply by a very simple and obvious manner, namely an element here is going to be just of the form some element of S divided by a power of xi, okay, and then what you do is you define the degree of a homogeneous element here is of the form a homogeneous element of S divided by some power of xi, and its degree will be the degree of the numerator minus the degree of the denominator, okay, that makes this into a graded ring, and then you take the degree 0 part, okay. So this is the ring of regular functions on this open subset of projective space. Mind you, on projective space a regular function is defined as something that is locally a quotient of homogeneous polynomials of the same degree, okay, whereas in affine space it's simply a regular function is simply a quotient of two polynomials. Of course it is supposed to be defined where the denominator polynomial does not vanish, right. So this is this isomorphism, and in fact so you know if I call the coordinates on this an as t1 t2 etc up to tn, then this isomorphism which is given by pullback of maps So the map is very simple. You give me a regular function here, its pullback is just composition with phi, so it's just f going to first apply phi, then apply f. So this is the pullback map, and this is an isomorphism. Okay, so moral of the story is that each of these ui's, there are n plus 1 of them. Okay, each of these ui's is just an affine space, affine n-dimensional space, and these n plus 1 affine spaces, they cover projective space, and the fact that this is an isomorphism actually tells you that the projective variety structure on projective space is given by gluing the affine variety structures on each of these affine spaces via these isomorphisms of varieties. Okay, so yeah, so there are I had asked you to check that this equality holds. Probably it's not so difficult to check that. So let me check this, and let me also tell you that in terms of rings, this isomorphism is given in a very nice way. This way it's given by a homogenization map, and this way it's given by a dehomogenization map. Okay, so let me just explain that. So the first thing that I want to tell you is that as to why the regular functions on ui are given by this ring. Okay, so so the situation is like this. So let me draw a diagram. So I have a affine space. So here is a n plus 1 minus the origin. This is the punctured n plus 1 dimensional affine space, and this is the projection onto the projective space. And here I have ui. Okay, and well, if you take pi inverse of ui, if you take its inverse image under this map, then you get pi inverse ui, which actually is, if you think about it for a moment, it is d of xi minus the origin. Okay, so ui in the projective space corresponds to the ith homogeneous coordinate xi not vanishing, and its inverse image above will correspond to the ith coordinate not vanishing. That means the equation, so you are looking at xi not equal to 0, and xi not equal to 0 is a basic open set d of xi. D of f always denotes the locus where f doesn't vanish. It's the complement of z of f, which is the locus where f vanishes, and we have already seen that d of f is itself an affine variety, isomorphic to an affine variety because of the Rabinovich trick. Okay, it can be so this d of xi can be embedded in an affine space of one dimension more, namely you can embed it in a n plus 2 as a closed subvariety. Okay, so this d of xi in the whole affine space is certainly it's an affine variety, and since I'm looking at its intersection with this, I have to throw away the origin. Okay, and that is the inverse image of this ui. Okay, and the point is that this map pi, so first observation is that this map pi itself is a morphism of varieties. Okay, see this map, this natural projection from the punctured affine n plus 1 dimensional space to the projective space, this itself is a morphism of varieties, and the reason is the reason is obvious because it is continuous. Okay, and a regular function here, if you give me by definition a regular function here is a quotient of two homogeneous polynomials. So if you compose it with pi, I will simply get a regular function here. So not every regular function here on an open set goes down to a regular function below. Okay, but regular function this map pi of course pulls back regular functions on open sets to regular functions on open sets. So it's obvious that pi is a morphism. okay. So continuity is obvious, and in one of the definitions you give this the quotient topology from that, okay. So this is certainly a continuous map, and if there is an open set here, what is a regular function on open set here? Locally it is of the form f by g, where f and g are homogeneous polynomials of the same degree. But if I take that function and compose it with pi, you know, if you pull it back, it will correspond to a function there, okay, and that function is of course it's going to be a function that's constant on lines. It's going to be a function that's constant on lines, lines passing through the origin, because that's what will happen. Any function on this set, when you compose it with the projection map, will give you a function above which is constant on lines through the origin, and conversely any function above which is constant on lines through the origin will go down to define a function below, okay. So if you take a function of the form f by g, f and g are homogeneous polynomials, of course defined on an open set contained in the locus where g doesn't vanish, then its inverse image will be simply the same function f by g, which is again a quotient of polynomials, and that's certainly a quotient of polynomials. A quotient of homogeneous polynomials is also a quotient of polynomials, and any quotient of polynomials defines a regular function locally on a fine space. So it's very clear that pi pulls back regular functions to regular functions. So pi is a morphism, okay. So pi is a morphism of varieties, and you know, therefore pull back via pi will give me a map from you know, regular functions here to regular functions there. So I'm looking at pi restricted to this, so I'm going to get O ui O of ui to O of pi inverse ui. This is what I'm going to get, and so namely you give me a regular function on ui, you compose it with pi, I will get a regular function on pi inverse ui. This is the pull back map, alright. So this is, and of course this is a K algebra homomorphism. Any morphism of varieties will induce a K algebra homomorphism which corresponds to the pullback of regular functions, okay. And of course mind you, ui is a variety now as far as our definition is concerned, because our definition allows varieties to be either affine or quasi-affine, or projective or quasi-projective. Ui is a quasi-projective variety. It is an open subset of a projective variety, in this case projective space, okay. And the point is that pi inverse ui is also a variety. Pi inverse ui is actually, you know, it's the it is just the this variety dxi. It's a basic open set. First thing is certainly if you take an element here is of the form f, it's of the form f by xi to the power of degree f, where f is homogeneous of certain degree, right. So an element of Sxi 0 is of the form f by xi to the degree f, okay. So Sxi S localized at xi is just inverting xi, so elements there will be of the form simply f by some power of xi. But then if I want degree 0 part, then I want the degree of this element to be 0, and the degree of this degree of a quotient is defined as the degree of the numerator minus degree of the denominator. So if you want that to be 0, then the power of the xi in the denominator should be equal to the degree of the numerator polynomial, which is supposed to be homogeneous. Okay, so this is how an element looks like, and this element is if you think of this element is of course a function which is constant on lines passing through the origin, because it's both the numerator and denominator are homogeneous of the same degree. In other words, it goes down to define a function on the projective space, and where it will define a function, it will define precisely a function on ui, because that is where xi is not 0. So it is very clear that clearly it is the pullback via pi of the regular function f by xi to the degree f, which is in O of ui. Okay, this is clearly a regular function on ui, because a regular function on projective space is supposed to be on an open set is supposed to be a quotient of polynomials, homogeneous polynomials of the same degree. So in this case it is certainly a quotient of homogeneous polynomials of the same degree. That is because you have taken it in the degree 0 part in the graded localization, and therefore it is a regular function. Okay, so what I am trying to say is that, you know, for the moment so you know I have so if I want to draw a more particular diagram, I have O so I have O of dxi in the affine space above. This is an affine variety, and you know that this can be identified with S sub xi. Okay, if you take dxi in the affine space, that is the locus where xi does not vanish, and it is an affine variety, its affine coordinate ring is Sxi. In fact, this is the same as AF, you can write A of dxi. The reason is because d of xi, the basic open set defined by xi, is of the form d of f, and every element of the form d of f is an affine variety, right, and its coordinate ring is just given by localization at f. So in this case, instead of f I have got xi. Okay, do not confuse it with the f here. Okay, so and you know you can see that certainly this is a sub of this. Okay, and what is happening is it is very clear that if I take an element, if I take an element of this form, it is certainly going to be a regular function on pi inverse ui. Okay, it is going to in fact be constant on lines. So it is very clear that this is going to sit inside this. All right, I want to say that, you know, if you go, there is a map like this. Okay, you start with an element here. An element here is certainly a regular function here. Okay, and it comes from a regular function here. Okay, so what I want to say is that, you know, so there is a map like this. Okay, so let me explain. So, you know, you start with an element here. This element is of this form. Now this element certainly defines a regular function here, okay, which goes down to a regular function there, and the pullback of that regular function is this regular function. Okay, so you have a map like this. Mind you, this is also an element of O of pi inverse ui. This is also an element, it is also a regular function there, and the same thing goes down to a regular function below, and if you pull back this regular function, you will get this regular function above. So when I write like this, here I am thinking of it as a regular function above on pi inverse ui. In fact, this makes sense as regular function on dxi. This certainly makes sense as a regular function on dxi. Okay, so when I write like this can be thought of as a regular function above. Okay, and since it is constant on lines passing through the origin, it also goes down to define a function, and that regular function is also given by the same expression. It is of the form one homogeneous polynomial by other of the same degree. Okay, so it is the same regular function that it defines below also. Okay, and and if you pull back this function below via pi, you will get this regular function above, alright. Here dxi minus 0 is the same as dxi because I don't have to remove, already origin is not there certainly, and the other thing is of course, so pi inverse ui is just dxi, and what I will have here is and this dxi will of course have affine coordinate ring sxi, of which if you consider it as a graded ring, the degree 0 part is sxi localized at 0, and the claim is that this map from, so this pullback map which goes from for regular functions on ui to regular functions on dxi, this map, the claim is that it factors through this, okay, and it factors through this and it's an isomorphism, that is the claim, alright. So so this is the claim, this is what one has to prove. So the argument is as follows, so any regular function on ui is locally of the form g by h, where g and h are homogeneous of same degree and with and defined in defined where h and defined where h is not 0, okay, inside ui. This is how, see, any regular function on ui looks like this. Locally it is of the form quotient of two homogeneous polynomials of the same degree, and it is defined where h is not 0 and it is inside ui, okay. See, its pullback via pi gives a regular function on ui on dxi, and hence it has to be of the form g by xi to the power of degree g, okay, because regular functions the regular functions on dxi, they have to be of the form g by xi some power of xi, and if they go down this power, if they go down to a function on projective space, the power of xi below should be equal to the homogeneous degree of the polynomial above. It has to be first of all any function, any regular function on dxi will look like some f by some power of xi, okay, but if it has to go down to a function on projective space, okay, then the numerator polynomial f has to be homogeneous and the denominator polynomial will be a power of xi, the power being equal to the degree of the numerator polynomial. Therefore since I am pulling back a regular function below, I will get a regular function above. The fact that it has come from below will tell you that when I pull it back it has to look like this, okay, and therefore this will also be the expression for the regular function below, okay, because this below g by h is on some open subset, okay, and this coincides with this on some open subset, alright, and that will tell you that it has to coincide on the largest possible open set, okay. So it has to be of this form. So maybe it may happen that there are some common factors, but so if you want I can put G1 here, I can put G1 by degree G1, okay, and this means that G1 by xi to the power of degree G1 is the same as G by h on all of ui, okay. So I am using the fact that on a variety, if two regular functions defined on a variety, if they coincide on an open non-empty open subset, then they coincide everywhere, okay. Therefore I start with a regular function here, I start with an element here, it is locally of the form G by h, okay. It may have locally many representations, but I am just taking one such representation G by h, okay, where G and h have to be homogeneous of the same degree. Now if I pull this function there locally to the affine space above, the punctured affine space above, of course I will land in dxi, okay, and locally on dxi I will get the regular function that I get by pulling back this regular function on ui will be a regular function on dxi, which has to be this, okay. Therefore the function I pulled from below has to be also of the same form, it is given globally in this form, okay. And so I'm just I mean this is just the statement that this mapping is surjective, okay. This shows that OUI to ODXI factors through SXI0 is both injective and surjective. I mean it is surjective, first of all the map from here to here actually lands in here, okay. The second thing is that it is surjective because if you take anything here it certainly defines regular function below, that is the first line that I wrote, okay. And it is injective for obvious reasons, because if a function above goes down to a function below, and if the function is if the function below is 0, then the function above you started with must be 0, and conversely if the function below is 0, if the function above is 0, of course the function it goes down to is 0, okay. So it is very clear that this is both, that this map is injective and that this map is surjective is very very clear, okay. So here what I am doing is I am using the fact that this is a morphism and this is and I am pulling back the functions, okay. But you can also think of it in another way by taking any element here which is an element of this form and that defines a regular function below, so you have also a map like that, okay. And then you can check that if you do it like that, then you are just defining the inverse map, okay. You start with an element here, it defines a regular function below, then you will get a map like this, okay. You can check that that map is also an isomorphism for the same reasons, okay. The only thing, the way I have done it is I've just used the pullback. I am just saying that this morphism which corresponds to the natural quotient of punctured affine space to projective space, if you take the pullback induces a k-algebra homomorphism, but that k-algebra homomorphism from the source to the target, it is injective, its image is precisely the degree 0 part. In other words, it is an isomorphism onto the degree 0 part, thus proving that the regular functions on ui is exactly this, the degree 0 part of the localization at xi is called which is called the homogeneous localization at xi, okay. So that is a proof of this statement, that these two are one and the same, and and to show that this pullback via phi, this map this is an isomorphism in terms of rings. You can actually give the ring isomorphism from K T1 Tn to this homogeneous localization. So what is that? So what is the other way? What is the other statement? So you see I have O of An and I have this isomorphism K algebra isomorphism, which is given by pullback via phi, pullback of regular functions via phi. This is supposed to give, as we proved last time, an isomorphism with OUI, but now you know this is K of T1 etc. Tn, and this is, as we have seen just above, it's just S localized at xi. So let me use a let me expand what S is. X is K x naught etc. up to xn, localized at xi, and then it's degree 0 part. Okay, this is S localized at xi, degree 0 part. And what is this isomorphism? What is a K algebra map in this direction? What is a K algebra map in this direction? This map is given, the map in this direction is given by homogenization, the map in this direction is given by dehomogenization, which is what we used in the last lecture to prove that this is an isomorphism. Okay, so what is a map in this direction? So you take f of or let me take P of T1 etc. Tn. What am I going to send it to? I am going to send it to the following thing. I homogenize it, okay, which means I take xi to the degree p of times p of x naught by xi and so on, xn by xi, and of course when I write this I omit xi by xi, alright, and I take this and and then I divide by xi to the degree p. Okay, see, if I take p, which is a polynomial in n variables, okay, and if I just take the numerator, this is the homogenization of p. It is, you add the new variable xi, okay, and then you get the homogenized polynomial. Now that will continue to have degree p, that will be homogeneous of degree p. Okay, here by degree p I mean the degree of the highest monomial here. Okay, the degree of a polynomial like this will consist of monomials, product of powers of ti, okay, and multiplied with some coefficients and sum of such finitely many such, and among them you take the monomials of the highest degree and take the highest degree and call that as a degree. Okay, there could be of course several monomials of the same highest degree, okay, but you take the highest degree monomial, okay, and call that as a degree of p. And if you take this expression on the numerator, what I will get is the homogenization of p. So this homogenization is achieved by adding a new variable xi, okay, and raising it to the degree p and multiplying it with this. Okay, now once I do this, the numerator becomes a homogeneous polynomial in x0 through xn of degree p, alright, and if I divide it by xi to the degree p, what I get is a regular function on ui, because a regular function on ui is of this form. It is some homogeneous polynomial in the x0 through xn divided by a power of xi which is equal to the degree of that homogeneous polynomial. So this is certainly an element of OUI. So this is how the map goes in this direction. You can explicitly write this map, okay, and what is a map in this direction? The map in the other direction is pretty simple, that is also very easy to write. So let us write that down, that is just dehomogenization. So what is a map in this direction? So this is pull back via pi, So I have here so let me write that k x naught etc xn localized at xi, take the degree 0 part, and here this is k t1 etc tn. We have this. So what is a map in this direction? The inverse map is you start with any g by xi to the degree g, okay, and what you will do is simply send it to g of t1 dot 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 1 tn. This is what you will do. So what you are doing is you are simply sending so this is dehomogenization, this is just dehomogenization, alright. So this g is a polynomial in x naught etc xi xn. G is a homogeneous polynomial in these n plus 1 variables, alright, and now what you do is in wherever xi comes you put 1, okay, wherever xi comes you put 1, okay, and for the remaining x naught through xn with xi left out, which are remaining n, you simply substitute t1 through tn. That is what this means. So this is dehomogenization. So this map is this is homogenization divided by the right power of xi. So this map in this direction is given by homogenization, and this map is given by dehomogenization, and therefore so the moral of the story is that and you can see that if I now start with this g and homogenize it and divide by degree g, I will simply get back this. So you can very easily see that this is the inverse of this map, okay. So what I am trying to say is that you see that this isomorphism of this ui with an geometric isomorphism, if you translate it to commutative algebra, it is just this isomorphism between a polynomial ring in n variables, okay, and a polynomial ring in n plus 1 variables localized at one of those variables and taking the degree 0 part, okay. The significance of this isomorphism, which you can write down just from commutative algebra, you do not need any geometry for that, okay. You can write this you can write these maps down just using commutative algebra, right. The fact that this isomorphism is an algebraic fact, and the geometric manifestation of that is that it is giving you an isomorphism of corresponding open subset of projective space with an affine space. That is what it means. So this is the commutative algebraic translation of this isomorphism, commutative algebraic translation of this geometric isomorphism, okay. And this is a very important theme in algebraic geometry. Whatever you see in terms of geometry, you should translate it to commutative algebra, and whatever you see in terms of commutative algebra, you should try to translate it to geometry, okay. And I am saying that in this case it is completely you can really write it down, there is nothing complicated about it, one is able to write down all the maps, okay. So so what I need to say is next, which I will do in the next lecture, is to tell you that I will use this to tell you that affine varieties are the building blocks of all varieties. So I will tell you that any variety can be covered by finitely many open sets which are each themselves isomorphic to affine varieties, okay. So affine varieties are the building blocks of all varieties, okay. So I will do that in the next lecture.